push on the top spot. Yeah, there you go.
At least wires. Can you guys hear me? Okay.
Yeah.
You can't hear me? You can? Okay.
Yes.
So my name is Dave Kuhn. I'm at Virginia Tech. My background is civil environmental engineering, and I'm going to talk today about oxygenation and aeration and recirculating aquaculture systems and other production systems like ponds and raceways. So the first thing is oxygen is critical for the health of fish and shrimp and other crustaceans. We all know that. Oxygen is required for life. Of course, fish use gills, and shrimp use a different kind of structure that's similar to gills. That's more shaped like a plate, which allows them to go like under the sand and come back up and breathe dissolved oxygen. Dissolved oxygen is basically oxygen from the ambient air that dissolves into the water. And we'll go into some details about what the saturation values look like in a few moments here. Oxygen in aquatic environments are also produced from plants, and in pond systems particularly, algae is a major producer of oxygen. Yes?
I don't think it's picking now. You just try to adjust the.
Oh, so that's volume.
I think it is over there.
It just popped out actually.
It's okay. It doesn't work.
Testing.
Oh.
There we go. All right. So oxygen is important for a lot of reasons. The most important reason is respiration. It's required for healthy animals. If you don't have sufficient oxygen in the water, they will be stressed out, and they'll put the energy that they have towards stress, trying to prevent disease and mortality. So you want to concentrate all that energy into production. That's the bottom line. So if you don't have sufficient oxygen levels, you have all sorts of issues in your system. Oxygen is essentially needed to break down food in cells. Without that, you're not going to have growth or healthy animals. And like I said, you really want to put all that energy into growth. Oxygen, in terms of water quality, keeps things aerobic. If you have anaerobic systems, you can have hydrogen sulfide production, which is toxic to the fish, and other issues as well. So if you ever have a recirculating aquaculture system, you smell like eggs, like rotten eggs, you may have a pocket somewhere in the corner of the system where oxygen is not getting distributed to that corner. So you have anaerobic bacteria growth that produces this toxin. So this is a pretty common graph you'll see. As you increase the temperature, the amount of dissolved oxygen in the water decreases. And so that's the maximum amount of oxygen in the water is called saturation state. And so you can see if you have a 30-degree tilapia, the maximum is around 8 milligrams per liter when you mix ambient air with water. And if you get down to, trout, might be like 15 degrees, you can see that the DO saturation values are a lot higher. Seawater also affects that. The ions of the salts limit the amount of oxygen that can dissolve into the water, so it's a little bit lower. So generally speaking, you want to maintain oxygen levels above 5 to 7 milligrams per liter, depending on the species. Tilapia, anything above 5 is fine. For trout, you might want, for salmonids, you might want to go above 7. When you start going below 3 to 4, depending on the species, you can have a lot of stress. I think tilapia, get below 3, 3.5. Trout, you start getting below 4, 4.5. You start seeing stressed out animals. And what that means is the fish start swimming slowly to the surface of the water, trying to get closer to the air to breathe. Their operculum, the outside the gills, may be fluttering faster, or even if they swirl and other signs of stress. So what I always tell my grad students is that you have all these different species of animals you work with in the lab. Watch them every day. When you feed them, watch their behavior, because if you see a change, that's the canary in the coal mine. It's going to give you kind of an indication early on that something's wrong. Anything less than 1 to 2, you have hypoxia, that's immediate death or severe stress environments. And so I would categorize anything less than 4, if we have long-term levels just below 4, for example, that can give a chronic stress to the fish or shrimp. And that can lead to issues like poor growth, the animals not feeding, disease outbreaks, those kinds of things. The acute, the short-term event that could happen is you go less than 1, they can just die from hypoxia, right? So the basics, I mean, you want to monitor. I don't care how small or big you are, you need to have a DO meter. I searched on Google and pulled the snapshot off the screen pretty fast. They're available everywhere. You have to calibrate them to the elevation that you're at. Obviously, stocking densities really matter. Water turnover in those tanks really matter. You want to efficiently feed. As you'll find out later when I talk about feeding, if you feed the fish, there's actually a DO demand. So if you feed the fish once a day, you're going to have a big DO demand. If you feed them twice a day, it's going to be separated into 2 smaller DO sags. And if you feed them more continuously during the day, you're going to have little bumps. So you have more stable DO. The first presenter talked about feeding the fish every 5 minutes for those reasons, to kind of stabilize the water quality, which includes dissolved oxygen. Obviously, we'll talk about aeration and water flow optimization as well in a few slides from now. So what is aeration versus oxygenation? Right, that's kind of the main question here. The title of this presentation is oxygenation, but really it's aeration and oxygenation. They're 2 different things. Aeration is a process of mixing ambient air with the water to dissolve the oxygen from the air into the water. So air is like 20% oxygen, and so it's as efficient as that. What we do is you'll see different systems. There's all sorts of systems. Walk to the trade show, do a Google search, you'll find tons of technologies out there. I'm going to give some basic examples. I could spend hours just showing you different technologies, but I'll just give a few examples. So, especially in pond systems, you're going to see surface agitators. For example, this is a paddle wheel. What you're basically doing is just kind of stirring up the water, splashing it, mixing those water droplets with the air, and as the air droplets go into the water, you have an air bubble going through the water, and that allows a lot of agitation, which allows the transfer of oxygen into the water. You'll see in this picture here, actually, that in this pond, you'll see that the direction of the flow from the paddle wheels is going in different directions, right? But if you kind of did a bird's eye view of this pond, you would see that it's probably a circular motion. So that also increases allows basically the dissolved oxygen in the system to kind of reach those corners if you have a flow movement like that. And these are not as intensive systems as RAS, so you don't have like a ton of fish in there that mess up the flow. You have a pond system where your flow of water actually needs more sometimes. We all know diffuse aerators. I'm sure we all have fish tanks or know people who have had them. I took two pictures here. You see the one on the left, you have some pretty coarse bubbles, and on the right, pretty fine bubbles. And so I would venture to guess that in theory, the one on the left is probably fresh water, and the one on the right is salt water. And so in the previous presentation, it wasn't talked about, but foam fractionators work really well in salt water because it has fine bubbles and it can attach to those really small dissolved solids and remove them. It becomes kind of like a sudsy thing. If you imagine, bubble size is really important. So you'll see people talk about the different technologies they have in diffusers, pore size, pressure, those kinds of things. And so if you imagine a 1 cubic foot bubble at the bottom of this floor going up through the water column to the ceiling, there's a certain amount of oxygen that transfers from that bubble into the water. And it's lower than it would be if you took that 1 cubic feet and put it into a bunch of small bubbles, because the specific surface area increases dramatically. And so if you imagine, if you had an infinitely tall water tower, that bubble would eventually dissolve away, right, and go into the water column. I took a class many years ago on hemodynamics, and I can't remember the numbers. I wish I could pull up the notes, but we did an experiment, a theoretical experiment, where we had how much oxygen transfer is from the bubbles into the water while it goes up through the water column versus what it does at the surface when it agitates that water. And the surface agitation actually is very important, probably more important if I remember correctly. So when you break that surface of the water,